Matt Fair, you claim to have the who, what, when, why of what is causing and driving Parkinson's from a mechanistic standpoint. Would you like to talk about that?
Yeah, I'll be happy to talk about it. It's a lot to get across, but it starts with genetics. It starts with understanding the disease. It starts with understanding and identifying the component parts of it, and figuring out what cells are most profoundly affected in the first place in Parkinson's disease. And I think we've figured that out from a genetic point of view. So where do I start with this? It's a long story.
Start
historically.
With, why should anyone listen to you?
All right. So people should listen to me because I've been working in this field for 30 years. I've dedicated pretty much my lifetime's effort of research to Parkinson's disease, trying to understand what causes it, with a view to trying to fix it, to try and put it right. It's a personal mission, one driven very much by my friends, and not so much by my family. There's nobody in my bloodline. My grandmother had Parkinson's disease, actually, but died a long time ago. But I've got too many friends with the disorder, and I've seen too much of it, right? And so I'm very passionate about figuring it out.
So your background is genetics, and as someone who's had the genetic testing done and it was negative, why is that not as important as I thought it was?
Well, you say you had the genetic testing done and it was negative, but I always ask people, did you get a report on all 21,000 genes? And the answer is generally no. And then I generally ask, so which genes did you have sequenced, and kind of what depth? And generally they can't answer that. Occasionally they may say GBA, or occasionally they might say LRRK2. But most people don't actually know. The genome's a very big place, and there are new variants being described all the time, and also new genes for Parkinson's disease being described all the time. Of course, it's date stamped. When you got your genome report done, that was probably some years ago, and things have moved on. There's been new genes since then.
Which brings me to a word that I kind of thought I knew what it meant, but also don't, which is penetrant.
Oh, okay. That's the probability of the phenotype given the genotype. That's easy.
What does that mean? So easy.
That means how likely is it that you're going to get the disease if you have a genetic variant that predisposes it. And that depends on the effect size, what's called the effect size of the variant of that particular mutation. Now in some genes, and some particular mutations, the effect size is huge. It's very, very large. And we call those causal genes or Mendelian genes, because you can see that the disease travels down the family line, goes from one generation to another. And typically Mendelian genes are quite penetrant. But then there's a whole load of very, very minor risk factors that are also genetic, that are associated with the condition. They're not genetically linked. You can't see them segregating down the family line with the disease. And they have very, very low effect sizes. They're not causal, they're associated.
So let's get to the question that we all really want the answer to, which is what actually causes Parkinson's?
So can I rephrase that? Instead of what causes Parkinson's disease, can I rephrase it, why does Parkinson's disease occur? What's the background for it? What's the basis of it? And I'd say that's pathogen defense. It's very simple as a concept, and you can see it in a whole variety of different ways. You can see it in a cellular way, for example, in the immune system and how the immune system deals with, say, infection. You can see it from the point of view of, for example, dopamine transmission, neurotransmission in the brain, doing imaging studies. It's all around pathogen defense. the part of the brain that's affected, the midbrain, it's in the brain stem in human beings. That part of the brain is very ancient. The hindbrain is very ancient. You can find the same part of the brain in, basically organized in a similar fashion in fruit flies, in zebrafish, even in some, maybe you can go as far as to say it's in a C. elegans, which is a worm that's about 1 millimeter long. It's very ancient, and the functions that it does are very ancient too. So, for example, there's a lot of autonomic functions that part of the brain controls. Things like gut peristalsis, how fast your gut moves, and leading to things like constipation when it doesn't move. Yeah, does that help? You need more?
Yeah.
Okay.
I guess
in a word, it's pathogen defense. But if you want me to get more detailed about it,
I think if I understand what you're saying is it's the body is trying to protect us from something.
Yeah. So if you look at genetic forms of Parkinson's disease that are causal, whereby you can say someone's inherited a particular variant and they're destined to get the disease, or they already have the disease because they have that particular variant. All of those forms of Parkinson's disease center around one particular type of biology, and that's autophagosome biology, which is involved in pathogen defense. That's a mechanism that immune cells have, that myeloid immune cells have, basically to manage the bacterial infection, whatever the infection is, or the insult. It doesn't actually have to be a bacterial infection, it could be a viral infection, it could be just an inflammatory insult, because myeloid cells respond to that. And there's a whole variety of them.
Could it be an environmental toxin?
It can be anything that causes inflammation. So it could be an environmental toxin like trichloroethylene or paraquat. It could even be a blow to the head, multiple concussions.
A virus?
Definitely a virus, yeah. COVID, all sorts of things. I liken Parkinson's disease, or the process that's occurring in Parkinson's disease, to kind of like waves on a beach. And if you think of a shoreline, and waves on the beach on the shoreline, it's the erosion of that shoreline over time that leads to the death of dopaminergic neurons. It's the lack of support that the dopaminergic neurons should have in their environment. If you don't support something in the environment, if it doesn't have a nurturing, supportive environment, it doesn't thrive and it might die. And Parkinson's disease is because dopaminergic neurons are in an environment, a glial environment, that doesn't thrive. And that starts in microglia in the brain, the resident immune cells in the brain, but it may actually start in the peripheral immune system. So it doesn't have to be necessarily in the brain. Myeloid cells are also found in the placenta, they're found in the bone marrow, they're found in the spleen, they're found in lots of different types of leukocytes in the blood.
Are they found in the gut?
Absolutely, loads. The entire gut lining is basically full of defense mechanisms against pathogens, because in the gut is a very, very hospitable place for the most part for bacteria to grow and divide. It's nice and warm, it's nice and moist. Bacteria grow there very, very easily, and you want good bacteria, you want good bugs, not bad bugs. So your bacterial lining, your gut lining basically produces an awful lot of compounds and chemicals to basically ensure that you have good bacteria rather than bad bacteria. There's a lot of immune cells, dendritic cells, macrophages, T cells, basically infiltrating, stopping pathogens from entering the bloodstream.
So you're saying Parkinson's is an overactive immune response?
In a sense, yes. You can liken it to an overactive immune response. I think of it more as an immune response that's happened and then not been turned off. So it's not that there's necessarily more of it, it's just lasting longer. And when you have an inflammatory problem, you often take NSAIDs, ibuprofen, whatever it is, to calm down the inflammation, and it makes you feel better. You need the inflammation to begin with. For example, you knock your knee or whatever it is, or you cut yourself. You need the inflammation to begin with. You need to feel the pain. You need to realize that this has happened. You need to see the rubor, the color. The blood flow needs to go there to basically deliver all the immune cells to fight off any invading pathogens, right? But as soon as that process happens, it needs to calm down. It needs to slow down. It needs to stop. Because if that inflammation stays hot, the rubor stays there, if those T cells keep invading and keep spraying cytotoxic kind of reactive oxygen species everywhere, the wound doesn't heal up. It just gets worse and worse and worse. And sometimes you get these kind of inflammatory crises. And in Parkinson's disease, I think the ability to be able to turn that off or dial that back down is perturbed. And the reason I say that is because there's a selective advantage to having a lot of the Mendelian forms, these causal forms of Parkinson's disease. They provide a selective advantage.
So you gave us the why. Can you give us the answer to reverse it or slow it down?
Can I personally do that? I can give you a direction. So I can give you a direction. I can tell you where to look. And I can do it through an evolutionary kind of perspective. So I think to solve the problem, you need to know what it is. You need to be able to define it. You need to understand the mechanism for it. You need to understand why it occurred, kind of where it occurred, when it occurred. You need to understand the reason behind the problem. And then you can fix it. You can fix it. And I think I know that direction.
Well,
yeah, amazing, isn't it?
yeah.
But it comes from an evolutionary point of view, because nothing in biology can be understood except through the lens of evolution. Right?
You heard it here first.
You certainly did.